So welcome back to our bridge course on mathematics, Vignan University. I am Dr. Sudam. So today we are going to discuss the matrices, right? Matrices is very interesting subject. People used to do very perfectly all the problems. Every units you leave, but matrices you will never leave. I know it, right? But some things are there. We need to know it. That I'll cover it here. And remaining things is just I'll tell you the small tips how to do the problem, right? So let us see the usage where we use matrices. Services like Netflix, right? So what you do there? In Netflix, what do you do? We used to see different movies. They maintain different databases like Amazon Prime, all these things. They use the matrices, right? To maintain different data in a particular way, right? So matrices are very, very important thing. So what movies to recommend to you? It compares your movie matrix with ones similar to yours and recommends movies that other users with your preferences also enjoyed. All these databases they will maintain and they use the process of matrix. Pretty much everything in computer graphics use matrices. Without matrices, there will be no video games. Video games are developed using the concept of matrices. Matrices are important method of storing diverse information, different types of information, diversity information, not even, right, analog, right, all these things they will be maintaining by using the matrices. Imaging also is very, very important thing. In image processing, right, matrix is a very, very important thing because that analog picture they will convert to matrix, then they will process it and they will again make to the picture by using the MATLAB or any other software, right? Everything they will represent in forms of matrix, then they will process it, right? This is also one more. Cryptography. So here also matrix is very, very important thing, right? Cryptography in the sense they will just encrypt the message, right? Ciphertext, they will encrypt the message and they will send to somebody so that nobody can track it, what is there inside. So to secure your message, right, that we call it the thing but the cryptography. So in that place also matrices is very much essential. Steganography. So hiding the message, right? Hiding the message with some video or some text, whatever the text you send, right? So they will encrypt with some image or some videos. That process we call it as nothing but steganography. There also matrices is very, very important. So studying matrices and their properties is of crucial importance in trying to improve linear solvers' efficiency as well as recognizing that the matrix enjoys a particular property and might be very crucial to develop a fast algorithm or even to prove that a solution exists or that the solution has some nice property. So each and every application matrices is very, very important things, but we may not aware of it. But everywhere we use the matrices, right? That will be coming slowly. You will be knowing where we are using the matrices for. Then what is determinant? What is the difference between the matrix and the determinant? Determinant is a value associated with square matrix. If it is square matrix, you are able to find the determinant. It's a value of a matrix. Value of the matrices is nothing but the determinant, right? Let us see. So matrix algebra has at least two advantages. What is it? It reduces complicated systems of equation, right, to simple expression. By using matrices, we can solve complications or different complications of that system of equation. We can solve it by using the matrix property. And I will tell you after this class. Adaptable systematic method of mathematical treatment and well suited to computers because it deals with the huge number of data. We can convert everything into the matrix. Everything in the sense all the analog things we can convert to matrix, right? Because computer reads only the numbers. So that numbers if you represent in forms of matrix, it will be easy for processing it, right? So that is why these are the two major advantages of the matrices. So a matrix is a set or the group of numbers arranged in a square or a rectangular array enclosed by two brackets. Very simple. What you are doing it? Enclosed by two brackets, right? Or any number, we can write it. Is it clear? Right? But can you say this 1, 2, 1, 2, 3 is a matrix? Yeah, can you say it is a matrix? No. So number of rows, number of columns, that must be uniform. Is it clear? So 1 to 1 corresponds. Then we can say that is a matrices. Some properties we will discuss here. So here, a specific number of rows and a specified number of columns, and two numbers, rows and column, describe the dimension or the size of the matrix. For example, you see 3 by 3 matrix. So 3 rows, 3 columns. Right? Here how many rows are there? 2 rows. How many columns are there? Right? 4 columns. So here how many rows are there? 1 row. How many columns are there? 2 columns. So that is nothing but the dimension of the matrix. Right? So a matrix is denoted by a bold capital letter A. Right? Bold capital letter A or B, bold capital letter will represent a matrix. So for example, you see m into n, there are m number of rows and n number of columns. So A11, A12, Ai up to Ain, right? A21, A22, Aij, A2n. So this is the representative general representation of a matrix. Is it clear? So this I is nothing but goes to 1 to m and j goes from 1 to n, right? So for example, let us take, I will say this is 1, 4, 6, 3, 4, 9, this is a matrix, right? So this 1 we can represent as A11, right? So this is nothing but A12, right? So this 1 is nothing but for row and this 1 is nothing but for your column, right? First row, first column. First row, second column, right? First row, third column. This is the way we are going to represent a matrix in general, right? So column matrix, how many types of matrix we will see? First one is your column matrix. If all the elements are arranged in one column, right, we call it as a column matrix. The number of rows may be any integer, but the number of columns is always 1. If only one column, here one column, how many rows? 3 rows. Here one column, how many rows? 2 rows, right? So that is nothing but in general we can write this one as a column matrix. Row matrix, any number of column, but the number of rows is 1, then we call it as the row matrix, right? Rectangular matrix, it contains more than one element and number of rows is not equal to the number of columns. Its size is rectangle, so the length is not equal to breadth, then we call it as a rectangle. Listen, the same way the number of rows is not equal to number of columns, so it is not a square, so obviously it is a rectangular matrix. See, like this, right? This is the column type, this is the row type, right? Here 2 columns are there but 4 rows are there. Here 2 rows are there but 5 columns are there. So m is not is equals to n in general, then we can call it as it's a rectangular matrix, square matrix. Let us come to the square matrix. So the number of rows is equal to the number of columns. See here, 2 rows, 2 columns, 3 rows, 3 columns. Then we can call it as a square matrix, right? When m is equals to n, number of rows equal to number of columns, right? So unit or identity matrix. See, everywhere 1 is there. Diagonal element is always 1. Then we can call it as in main diagonal always 1 should be there. Then we can call it as the unity matrix or identity matrix, right? Null matrix, all elements are 0. If all elements are 0, what is the use of null matrix? You might be thinking about it, right? So there are a lot of application of the null matrix also. We'll discuss later, right? Triangular matrix, right? So a square matrix whose elements above or below the main diagonal are 0. See here, this is your main diagonal and all are 0 here, right? This is the main diagonal matrix, all are 0 here. This is the main diagonal and all are 0 here, right? This is what? Lower triangular matrix, lower it is 0 and here upper elements are 0. So that is why any type of a square matrix whose elements above or below the main diagonals are 0, we call it as the triangular matrix, right? Upper triangular matrix. Upper triangular means, see, this is your upper triangular matrix. So this part will be 0. Here this part will be 0. Below the below the main diagonal will be 0. Then you can call it as your upper triangular matrix, right? Lower triangular matrix, this is the lower triangular matrix. So this part of elements will be 0, right? They have much more applications. Scalar matrix. Scalar matrix means, you see here, a diagonal matrix whose main diagonal elements are equal to the same scalar, right? So here a scalar is defined as a single number or the constant, any number, 4, 4, 4. Let us take see. A scalar matrix with 1 in its diagonal is nothing but your identity matrix. Instead of 1, if you put 2, then what happens? 2, 2, 2 and remaining are 0, that is nothing but a scalar matrix. If you multiply 6 with it, then it will become 6, 6, 6, that is nothing but a scalar matrix. Is it clear? So if diagonal matrix other than 1 is there, in diagonal elements other than 1 is there, then that is nothing but the scalar matrix. And 1 is there, we call it as the identity matrix. So identity matrix is a nothing but a scalar matrix. Is it clear? Now equality of matrices. When two matrices will be equal? Two matrices are said to be equal only when all corresponding elements are equal, right? If two matrices, we call it as equal if everything is equal. If one is unequal, we cannot see unequal, right? 1 0 0 2 1 0 5 2 3 1 0 0 2 1 0 5 2 3 everything. So there is no other process to make it equal. Each and every element should be equal only, right? So there should not be any confusion regarding this. Some properties of equality. If A equal to B, then B equal to A for all A and B. If A equal to B and B equal to C, then A equal to C for all A, B and C. Is it clear? Right? Addition and subtraction of matrices. The sum or the difference of two matrices A and B of the same size yields a matrix C of the same size. Same size means dimension is same. If you are adding two matrices of same size, means 2 by 2 or 2 by 2. So the resultant matrix also of the dimension of 2 by 2 only. So Ci is equal to A is A plus B is A. So matrices of different sizes cannot be added or subtracted. Note, you should remember it, right? So it means what? 1, 2, 3, 4 is one matrix, right? Plus if I will do 1, 2, 1 and 3, 4, 6. So can you add it? Never. Because this is 2 by 2, right? This is 2 by 2 matrix, and this is how many rows? 2 rows, but 3 columns are there. So this cannot be mapped. Is it clear? So addition can be done, right, if their size is equal. So A plus B is equals to B plus A. So addition or subtraction, addition is always commutative. So associative law, if A plus B plus C can be done like this, right? So this is nothing but your associative law. So for example, I have given, I think you know it, so I need not explain it, right? Two matrices we have given and we have tested that this A and B and this is C, right? Just simple addition it. So A plus 0, 0 is nothing but your null matrix. If null matrix is added to the any matrix, you will get the same matrix. So A plus 0 equal to nothing but 0 plus A. A plus minus A is always nothing but a null matrix. This 0 is not simple 0, right? This 0 is nothing but not simple 0. It's a null matrix. So every element of the matrix is 0. If A is of 2 by 2, then the null matrix also you should get a 2 by 2 when you do the addition of it, right? Scalar multiplication. If you multiply any constant to a particular matrix, right? So that will multiply to each and every k into A equal to A into k, where k is a scalar. Is it clear? Right? So if k is equals to 4, then what happens? 4 will be multiplied to the element. So 4 into this matrix. Right? See, 4 should be multiplied to each and every element of the matrix. Is it clear? So 4 3s are 12, 4 into minus 1 minus 4. So every element should multiply with the 4. 4 is a multiply, you should not multiply a single element, you should multiply the each and every element. Is it clear? See, some properties, k into A plus B is equals to ka plus kb. So k will multiply to A plus k will multiply to B. If k plus g into A is equals to k into A plus g into A, where k and g are two different scalar. So k into AB is nothing but ka into B, that can be done. So k into GA is nothing but kg, we can multiply it and you can multiply with the matrix direct, right? So multiplication of matrices. This is very, very important thing, and maximum time I have seen you do the mistake here. Even though you know it, when you do the multiplication, you do it several mistakes, right? See here, the product of two matrices is another matrix. Obviously, two matrices will multiply, obviously we will get another matrix. But the type of matrix you need to take, two matrix A and B must be conformable or comfortable, or they should match. In how? For multiplication to be possible, right? If the number of columns of A must equal to the number of rows of B, the column of a first matrix will be equal to the number of rows of the second matrix, then only it is possible to multiply, other it is not, right? So A into B always is C. See, 1 into 3, this is the, how many? First, how many? 1 row, 3 column, right? Here 3 rows, 1 column. So what you have written? The number of column of A, how many number of column? 3, right? Must be equal to the number of rows of B. How many rows here? 3, right? So this must be equal to multiplied, right? Is it clear? Then only. But when what will be the product you will get? The matrix, the resultant matrix will be 1:1. So this is the magic here, right? So B into A is not possible. Why? This is not equal. They are not compatible, right? 6 into 2, if you take one matrix, another is 6 into 3, it is not possible, right? So this must be equal, right? A into B equal to C, where A is a 2 by 3 matrix, B is 3 by 2 matrix, the resultant will be always 2 by 2 matrix. This is possible because the number of rows, right? The first one is, this is the compatible part, right? Is it clear? Yeah. So matrices operations, how do you multiply it? So this into this, right? And this into this is the way you need to multiply it. So this is the what? This is how many rows are there? 2 rows are there. How many columns are there? 3 columns are there. Here how many rows are there? 3 rows are there. And how many columns are there? 2 columns are there, right? So this is a compatible part. So the resultant matrix will get a 2 by 2 matrix. Is it clear? Right? Matrices operation, this is nothing but if you multiply any identity matrix to a particular matrix, then you will get the same matrix, right? So the matrix will never change. For example, 1 0 0 1, if you multiply this, you will get the same matrix for it. Assuming that the matrices A, B, C are conformable or compatible with each other, right, based on the previous rule. Okay, so IA is nothing but identity matrix. If you multiply it to the matrix, you will get the same matrix. A into BC is equals to ABC is equals to ABC. This is associative law. A into B plus C will be AB plus AC, right? A plus B plus C is nothing but AC plus BC. Caution, remember, note down it. A into B not generally equal to BA, and BA may not be conformable, may not be compatible. This is the very, very important thing. So AB is not equal to BA, they are not commutative. If AB equal to 0, neither A or B necessarily 0, right? If AB is equals to 0, if A is a matrix and B is a matrix, if you multiply these two, if you are getting 0, it doesn't mean that either A or B is 0. Is it clear? But if I write two numbers A into B is equals to 0, this is a number and this is a number, right? If it is 0, then in number system, either A or B should be 0 to make the product 0, but in matrix it doesn't happen. Is it clear? So if AB equal to AC, B not necessarily C, right? If A, this is never happen because division in matrices is not allowed. Is it clear? Because of this property. If this property holds, then division will be allowed in that. Is it clear? So A you cannot cancel it, right? That is the very, very important things here. Matrices operation. This is just one example. AB not generally equal to BA. See here, one you have taken one matrix T, another matrix you have taken T into S. If you multiply T into S, you are getting this one, right? And if you are multiplying S into T, you are getting this one. So both are not equal, right? That is the proof here. If AB is equals to 0, neither A or B necessarily 0. See, this is the matrix A, this is the matrix B, and A is not a 0 matrix, B is not a 0 matrix, but product I got 0. Is it clear? So that is why when you are multiplying two matrices A and B, and if you are getting 0, it doesn't mean that A is a null matrix or B is a null matrix. So A and B need not be a null matrix. This is very important. Is it clear? Right? Now let us go for transpose of a matrix. If A equal to 2, 4, 7, 5, 3, 1, let us take. Then transpose of denote the transpose. The row will be converted to column and column will be converted to row. Is it clear? Right. So you know it better. Interchange rows and columns simply. Right? The dimension of the A transpose are the reverse of the dimension of the A. If it is A is 2 by 3, then A transpose is nothing but 3 by 2. So let us take this is A and A transpose is got. This is the dimension of A and this will be the dimension of A transpose. Properties, some properties let us know. A plus B whole transpose equal to A transpose plus B transpose. A into B whole transpose equal to B transpose into A transpose, because, right, this is possible. Is it clear? Right. So K into A transpose equals to K into A transpose. A transpose of transpose is nothing but your A. It comes to the original position. So now these are the certain example, you can test it. I don't want to explain all these things to you, right? So A I have taken 1, B I have taken 1, right? I have done the A plus B, then I have transposed it, right? So then what next what I have done? A transpose I have done, B transpose I have done, right? I have just added it, you got this value. Now see this, yeah? So what happens? These two are equal, right? These two are the equal matrix. So matrix operations. The same whatever I have told you in the properties, just I have given with some example and testing it. So A into B whole transpose is nothing but B transpose into A transpose. So two matrices I have taken, I have just multiplied it and got the same value. Is it clear? Now symmetric matrix. A square matrix is symmetric. A square matrix is symmetric. If it is not square, we cannot go for any symmetricity. So if it is equal to its transpose, it means what? If A equal to A transpose, then we call it as, that is a symmetry matrix, right? To know the symmetry, symmetry can be possible only for square matrix, right? When the original matrix is square, transposition doesn't affect the elements of the main diagonal. If it is a square matrix, A, B, C, D is there. So this AD is fixed here. This AD is fixed here. So the identity matrix I is a diagonal matrix of D. Identity matrix, if you make it transpose, then what happens? The same thing will be coming again. So now inverse of a matrix. So consider a scalar K. The inverse is reciprocal of it, right? So K inverse is 1 by K, and K into 1 by K is nothing but what? 1, right? So if K is 7, if K equal to 7, inverse of 7 is how much? 1 by 7. Division of matrices is not defined, since there may be AB equal to AC doesn't hold, because if AB equal to AC, then B and C need not be equal. So that is why division of matrices are not allowed. So that is why we use in a different way. Instead of matrix, inversion is used. So that is why the A inverse of A is nothing but it doesn't know that 1 by A. We cannot do this in matrices, right? Inverse of 7 is 1 by 7. It doesn't mean that inversion of A is nothing but the 1 by A. Is it clear? This doesn't hold because of this property. I have already told you previously. So instead of matrix, inversion is used. The inverse of a square matrix A, if it exists, is the unique matrix. Is the unique matrix. If it is, when it is possible, if A into A inverse is A inverse into A must be equals to A identity matrix. So if any matrix is there A, and if any other matrix is B, let us take, and if you are multiplying these two, you should get an identity matrix, then B can be called as the inverse of A, right? So matrix operations, right? Okay, we will tell this one, the properties of the inverse. So AB inverse equal to B inverse, A inverse. A inverse of inverse is nothing but your A. A transpose inverse is nothing but A inverse whole transpose. So K into A, these are the different properties of the inverse. So when the determinant of a matrix is 0, the matrix is called singular matrix. Right? And for singular matrix, you cannot find an inverse. Remember this. So inverse can be found out for a non-singular matrix. Non-singular means what? Determinant should not be 0. Determinant of a matrix is 0 means we cannot find the inverse of a matrix. Right? So a square matrix that has an inverse is called a non-singular matrix. Is it clear? So non-singular matrix means determinant is not equal to 0. If determinant is equal to 0, we call it as singular. For singular matrix, there is no inverse. For non-singular matrix, we can find out the inverse. Is it clear? Right. That is what I am going to say. Determinant. What is determinant? Right. So to compute the inverse of the matrix, we need to depend on determinant. Right. So each square matrix A has a unit scalar value. That is nothing but the determinant. Every matrix, every square matrix, determinant can be find out for only square matrix. Inverse can be find out for a square matrix. So determinant is nothing but the value of a matrix. It is a scalar, simple scalar, a single number. That is nothing but determinant. Is it clear? So determinant, how do you write? Simple line. But matrix, how do you write? Either in the square bracket or open bracket, right? But this is nothing but matrix. How do you evaluate the determinant? 5 into 1. 5 into 1 minus 6 into 2 is equals to how much? Right? That is nothing but your determinant of it. Right? So using the adjoint of the matrix, right? You know what is adjoint, what is cofactor, right? What is minor. Based on this concept, you can find out the inverse. And there are various methods to find the inverse of the matrix also. We will discuss elaborately when it comes to your main program. This one already done it. How to find the inverse by using the adjoint, cofactor, minors, right? And you get it. So the matrix of R rows, what is the rank of a matrix? What is rank of a matrix? A matrix of R rows and C column is said to be of order R by C if it is a square matrix R by R. Then the matrix is of order R. So the rank of a matrix equals to the order of the highest order of non-singular submatrix. What does it mean? Let us take, this is the matrix 2 by 3. I'll give one example. See. So R equal to 1 to 4 and 2, 4, 8 is given. 3 square submatrices are there. How many submatrices you can find out from this? That is nothing but the minor. Is it clear? Right? So R1, R2 and R3, we found 3 submatrices of this. Right? Each of these has the determinant of 0. So the rank is less than 2. 2 by 2 matrix given 0 determinant. Has determinant is 0. So 2 cannot be the rank of it. If 2 cannot be the rank of it, then what is it? Obviously it is 1. Because this is what? How many rows are there? 2 rows. How many columns are there? 3. Right? And it depends on the rows. So if 2 is not the rank, then what is the rank? 1. That is why we have to decide like this. So there are many processes there to find the rank of the matrix also. So rank using elementary transformation. What is elementary transformation? Right? Is it clear? See here one example is there. You heard 1, 2, 4, 2, 4, 8. Right? 1, 2, 4, 2, 4, 8. Right? I will do the elementary transformation and show you that this is the, without finding any minor cofactor, we can find the rank of it. And this process is very, very important thing to implement anywhere. Right? See, 1, 2, 4, 2, 4, 8 is there. Is it clear? So what you will do now? Right? So elementary transformation you have to find out. Elementary transformation, how do you find the rank means? You need to convert either to echelon form, right? Or you need to convert to normal form. You need to convert to normal form. Right? So echelon form means all the elements of lower the main diagonal will be 0. And the normal form means all the elements of the upper element of main diagonal and the lower elements of the main diagonal should be 0. Right? So this is nothing but the echelon form, this is nothing but the normal form. So we have to convert all these things to, right? We have to convert all these things to in this two model. One is echelon form and another is your normal form, right? So just I'll give very simple process how to do this, right? Later we'll go for this. So 1, 2, 4. Echelon form means how it should be. First of all, it should be 0. Is it clear? First of all, it should be 0. Then what we'll do? We'll do some row multiplication, row transformation, right? So I'll write here, right? So R2 minus 2 into R1, right? Then what will get? 1, 2, 4. 2 minus 2 is 0, right? So 4 minus 4 is 0. 8 minus 8 is 0. Is it clear? We are multiplying here. So 2, 4, 8. R2 minus, what is R2? 2, 4, 8 is R2. Minus, what is R1? We are multiplying 2. This is R1, right? And this is your R2. I am multiplying 2 here. 2 multiplied. So what will get? 2, 4, 8. So what will get? 0, 0, 0. That is what I have written here. So one row vanished at all. So only one row remained. That is nothing but the rank. So in echelon form, how many non-zero rows are there? That is nothing but your rank. Or in normal form, how many non-zero rows you are getting? That is nothing but the rank of the matrix. Is it clear? That is the way you need to. There are various processes that we will discuss elaborately, but this way will be helpful to you in each and every places, right? So that is what. So thank you very much, right, for the session. So next class we will go for the different topics, right? I hope you understand well. So thank you very much for this.